Hello students, welcome to lecture number 8 of computer architecture course. Today we are going to look at floating point arithmetic and floating point adders. So this lecture is basically divided into two halves. In the first half we will see and learn how floating point arithmetic works, what are the different representations of that, how is it different than normal integer based arithmetics, and once we have an idea on its representation as per the IEEE standards and the definition and its differentiation with the regular integer arithmetic, then we are going to move forward and try to do additions using that notation, and the eventual goal is to build a circuit for the floating point adder. Okay, so that's how the things will work. Okay, so in floating point arithmetic, the first question that I would like to ask everyone, why do we really care? I mean, why do we care about floating point numbers? First of all, why is it so important? Right, so the first thing is providing hardware support for floating point arithmetic is very crucial. That is highly imperative that we provide hardware support for such arithmetic operations, because we already have hardware support for integer based operations, but we do not have hardware support for floating point arithmetic. So it is important to build that up. You will also comprehend how to represent floating point numbers in the processor, like how does exactly the processor handle such floating point numbers, how to perform arithmetic with floating point numbers, like how do we do addition, how do we do other sort of arithmetic operations using floating point numbers, and learning to use floating point arithmetics in MIPS. That's also something that we should care about. So IEEE format for single and double precision floating point numbers is one of the most important objectives of this lecture, to learn about that. Secondly, we will also learn about floating point addition and multiplication. Multiplication, of course, you may have already learnt about it a little bit, and you know what a floating point multiplication or multiplier does, and support for floating point computations in MIPS. So these are the things that you will have a chance to learn by understanding the concepts of this lecture. Now let me tell you some basic definitions before we move forward. Okay, one of the first things that I would like to mention is what is floating point, how do we define. So computer arithmetic that represents numbers in which the binary point is not fixed is called a floating point. Fine. So that is the first definition of what is a floating point. The second definition that I would like to mention is, in a floating point you will always have a component of exponent. So what is exponent? In the numerical representation system of floating point arithmetic, the value that is placed in the exponent field of the representation is called an exponent. Okay. The third definition that I would like to move on to is called scientific notation. This is also very frequently used in the context or parlance of floating point arithmetic. The notation that renders numbers with a single digit to the left of the decimal point is called a scientific notation. Okay, that means you will have a single digit to the left of the decimal point, then it is called a scientific notation. Of course you will have a component of exponent that will be together. We will see how to represent that in the next slides. The fourth definition is what is a normalized scientific notation. So a number in floating point notation that has no leading zeros is called a normalized scientific floating point notation. Right. So I had told you 4 crucial definitions in the context of floating point arithmetic. Now also let me remind you of the fact that from a designer's perspective who wants to build a hardware for this in MIPS, a designer of a floating point representation must find a compromise between the size of the fraction and size of the exponent, because a fixed word size means you must take a bit from one to add a bit to the other, right? So there is a trade-off involved, and this trade-off is between the precision and the range, isn't it? So there is a sort of a trade-off between the precision and the range that you have decided for. And increasing the size of the fraction enhances the precision of the fraction, while increasing the size of the exponent increases the range of the numbers that can be represented. Okay, so that's how we have a trade-off between precision and range. So what did I say? A scientific notation is a notation that renders numbers with a single digit to the left of the decimal point. That's how we define scientific notation. And a normalized scientific notation is a one in which there are no leading zeros to the left of the decimal point. So you could see the example below. 1.0 into 10 to the power minus 9 is a normalized scientific notation, right? Because we don't have leading zeros to the left of the decimal point. On the contrary, 0.1 into 10 to the power minus 8, which is the same representation of the above number, right? Which is the same representation of the above number. You see that there is a leading zero. So we will not call this as normalized. We will call this as scientific notation. Now, an IEEE floating point representation consists of three components. Now, it is very important to note the word IEEE floating point representation. Why? Because all the representations that we are going to talk about in today's lecture has been regularized and standardized by IEEE 754 standard. Okay. So these are all defined and standardized by IEEE. So therefore, IEEE floating point representation consists of three components. The first is a sign bit, second is an exponent, and third is a mantissa, which we also called significant, which is assumed to be 1 point and then the numbers which are at the right of the decimal. Okay, so this is called a normalized representation because we don't have any leading zeros, as I said in the last slide. There are two types of IEEE 754 standard representations. The first is single precision, which is a number that is 32-bit, and we have double precision, which is a number which is 64-bit. So as you could imagine that in the double precision, of course the precision and accuracy is much more, okay, but you require more number of bits. Okay, the range is large, you require more number of bits to store that particular number or represent that particular number in that particular format. Now let's see how an IEEE floating point format looks like. So this is the specific format that I'm talking of. You will have a sign bit, a sign field rather, then you will have an exponent field, and you will have a fraction field. Okay, so the exponent in single precision format is 8 bits, while the exponent field in double precision format is 11 bits. The fraction in single precision format is 23 bits, while the fraction in double precision format is 52 bits. So any number x, decimal number x, can be represented as follows: -1 to the power s multiplied by 1 plus fraction together multiplied by 2 to the power exponent minus bias. Okay, so here s is a sign bit which can be a 0 for non-negative numbers and it will be a 1 for negative numbers. Okay, and the range of signed 8-bit can be from -127 to +127 because it's an 8-bit number, which is equivalent to 0000 in binary to 1111. And so if we want to represent -127 in bias notation, we will have to add a bias of +127 to make it 0, right? So -127 plus 127 gives us 0, which is a number which is from 0 to 255, right? -127 to +127, which is equivalent to 0 to 255, right? -127 plus 127 gives you a 0, and 127 plus 127 gives you 254. We will have one digit for some special purposes, right? So therefore the exponent is equals to actual exponent plus bias. That is, actual exponent is given by exponent minus bias. That's why I put 2 to the power exponent minus bias. While the formula for the exponent is actual exponent plus bias. So how do we calculate the bias? Biasing is given by the formula 2 to the power k minus 1 minus 1, where k is the number of bits in the exponent field. So for single precision IEEE 754 format, the bias is 127 because the value of k is 8. So 2 to the power 7 minus 1 gives 127. And for double precision formats, the bias is 1023. Here the value of k is 11. So it will be 2 to the power 10 minus 1. Okay. Okay, now let's move to an example. So as IEEE single precision floating point representation example could be as follows. As I said, if you fill in the values of the generic formula which I spoke in the last slide, it will be minus 1 to the power s into f plus 2 to the power e minus 127, because biasing is 127 here. Fraction is 23 bits, exponent is 8 bits, sign is 1 bit. So the total 32 bit representation will look like the one shown in the below figure. 1 bit is for the sign bit represented in green. Okay, sky blue is the one that you have for the exponent field, which is 8 bit, and then you have 23 bit for the blue color, the light blue, which is 23 bits. So in total it makes up 32 bit for IEEE single precision floating point representation. Similarly, the IEEE double precision floating point representation can be shown as follows. Minus 1 to the power s into f into 2 to the power e minus 1023. The fraction bit is 52 bits. Mind it, in the previous case the fraction was 23, now it is 52 bits. The exponent field is enhanced to 11 bits from 8 bits. Sign bit remains as it is. So therefore the green color is for sign bit, the sky blue exponent is 11 bits, and the light blue is for the fraction, which is 20 bits in the first 32 bit, and then 32 bit again for the next 32 bit representation. So here we actually are representing that using two 32 bit registers. Okay, so the first 32 bit register has 20 bits from the fraction, 11 bits from the exponent, and 1 bit from the sign, and the next 32 bit register has completely all 32 bit reserved for the fraction representation. Okay, so therefore the fraction becomes 20 plus 32 equals to 52 bits, right? Now let us try one example. Let's see how this is actually done for some real numbers, real time numbers. So say I want to represent a number which is minus 0.75 or 75 in decimal in single precision and double precision format as per IEEE 754 binary representation. So minus 0.75 is represented as minus 0.11 in binary. In scientific notation, the value is minus 0.11 base 2 times 2 to the power 0, right? And we will have to convert this to normalized scientific notation because we have a leading 0. So in normalized scientific notation, the value is minus 1.1 base 2 into 2 to the power minus 1, right? So we have shifted the number to the left, as a result of which the exponent value has decreased. From 2 to the power 0 it has become 2 to the power minus 1. From minus 0.11 it has become minus 1.1 because of shifting of the fraction part to the left. Okay, so now by going by the generic representation for a single precision number, it is minus 1 to the power s into 1 plus f into 2 to the power exponent minus 127. So now if we subtract the bias 127 from the exponent, right, so what is going to happen? We will have a number. So because we wanted to get a number minus 1, which is the actual exponent that we are talking about. So in this case the exponent will be 126. If you just put in the formula in the actual exponent, if you just put in the formula of -1 and in place of the exponent you want to find out what that number will be, biasing is anyways 127, right? So it will be -1 plus 127, so the exponent will be 126. So that is the number we put here, 126. That is the exponent field that we will be representing. So now going by that, now -1 to the power 1, because it's a negative number, so the sign bit is 1, so therefore s is 1, times 1 plus f, the fraction part. The fraction part is the number that we want to represent that as. Now the fraction part that you already saw is 0.1, right? So 0.1 you already have seen it here. This is 0.1 here in this representation. So if you just put 0.1 plus 0.1 and all the remainings will be filled up until you have 23 bits in total. So 3 plus 4, 7, 11, 15, 19 and 4, 23. So that's why we have all the numbers to the right of the decimal, 23 bits, which represents the fraction part. And this totality, in totality the number inside the bracket from 1 plus the entire quantity that you see for the fraction gives you the significand. And of course 2 to the power 126, which is what I just spoke some time back, which is the number in the exponent field. If you just put actual exponent as -1 and bias as 127, you're going to get 126. So going by this representation, the single precision format now can be as follows. You have, for sign, this 1 comes here because it's a negative number. The exponent 126 binary representation is put here in 8 bits, and all the remaining 23 bits that you have here is from this to this, 0 to 22, this part. This is the fraction part. Okay, so and this entire representation is called single precision format. The same number, now if you want to represent as a double precision floating point representation, what we are going to do is we will have to recalculate the value of the exponent using the same formula, right? So in this case the value of the exponent will be 1022 because we want a -1, so the exponent value will be 1022 minus 1023, which gives you the 1022 as the exponent value. Now if you convert that binary representation of 1022, it will be the number that is shown here, 0 1 1 1 1 1 1 dot 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 1 0. So this is the 11-bit binary representation of 1022. And if you just traverse till 52 bits for the fraction part, it will be 0.1 and then the rest will be all filled to zeros until you have 52 bits. So here 20 bits and all the bits of the next register, 32 bits, will all be zeros, and sign bit will not change because it's a negative number. So the light blue portion becomes the fraction 100 till you have all zeros, and the sky blue portion becomes 0111 dot dot 10 and the sign becomes 1. So that's how the double precision works here. The biasing, as I said before, is 11 bits for double precision format. Now let me talk about converting a floating point representation to decimal number. So now let us do the reverse of what we were doing. Imagine you are given a floating point representation and you have to convert that to a decimal number. So what will you do in that case? So if the bits of the fraction are numbered from left to right, such as s1, s2, s3, then the value is -1 to the power s times 1 plus s1 into 2 to the power -1 plus s2 into 2 to the power -2 plus s3 into 2 to the power -3 dot 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 until you have the number of bits multiplied by 2 to the power e, with the significand is 1 plus fraction. Okay, so imagine that you have a single precision floating point representation that is shown here. Now going by the representation, if you just try to convert the fraction element into its corresponding decimal representation, you will see that for the one that you have in the fraction part, this one, that will be multiplied by 2 to the power minus 2, because this s1 is 0 for this and all the remaining ones are zeros. So only for the bit 1 here, which is substituted in place of s2, you get 1 into 2 to the power minus 2, which is 1/4 equals to 0.25. So now going by the basic equation, minus 1 to the power s multiplied by 1 plus f multiplied by 2 to the power exponent minus 127. So it becomes minus 1 to the power 1, right, because we have a 1 here, multiplied by 1 plus 0.25 is 0.25 is coming for this fraction part that you have already computed, into 2 to the power of 129 minus 127. So this 129 is the decimal of this exponent binary that is here. So that goes here. So the actual exponent is 2, 129 minus 127. So 2 to the power 2 gives 4, and this entire computation becomes minus 5.0. So this is the equivalent decimal representation of this IEEE 754 floating point representation. Right, so you understand, right? So what we are doing, we are just converting from floating point to decimal instead of converting from decimal to floating point. We are doing the reverse process here. Now let me move forward with the floating point addition. So far you have already learnt about what is a single precision format, what is a double precision format, how to represent that in IEEE 754 layout. Why do we add biasing? Okay, because we wanted to make it a signed number. Okay, like as I said, if you have a number between 0 to 254, instead of going from 0 to 254, you will add bias to that. So if it's a minus 127, so that becomes 0 because of adding plus 127 to that. And if it becomes if it's a plus 127, you will add plus 127 to that, it becomes 254. So instead of dealing with this negative and positive representations, we will convert everything between 0 and 254. I'm just giving an example for 8-bit numbers, similarly for 11-bit numbers. So therefore biasing is important. How do we calculate biasing? What are the biasing range? That also you know. How to handle the trade-off between range and precision, that is also now clear. Okay, so now you've got a pretty much an idea, and also we've learned about how to do the conversion process from floating point to decimal and vice versa, decimal to floating point also. So since all of these bases are now cleared, this base is cleared, so now we will move forward with the floating point addition. So let us generically have a look at what are the major steps. There are 4 major steps when we do floating point addition. First is to compare the exponent. That is very crucial. That is, we need to compare the exponent and do something. What is to do with that? We will shift the smaller number to the right until the exponent would match the larger exponent. Okay, and then we will add the exponents, or add the significance, not exponent really, add the significance once we do the shifting. So first is comparing the exponent of two numbers, then shifting the smaller number to the right until the exponent would match. That is the first step. Once it is done and both the exponents are matching to each other, then we will add the significance. In the third step, we will do the normalization, that is either shifting right or and incrementing the exponent, or shifting left and decrementing the exponent. We will check for underflow overflow, that is if it fits within the given amount of bit size. If there is a problem, then we'll have an exception to handle it. If not, then we will round the significant to the appropriate number of bits that are provided to us or assumed, and again check for normalization. If it is normalized, then we will stop. If not, then we will again go back and do the normalization process. So that's pretty much the flowchart of the floating point addition that is usually used. So I think I'll stop here, and I'll pretty much go and ask about the questions that you have and the doubts that you have, and then we can move to the next part of the lecture. Thank you.